Hi, this is Jeff Gorey, the Principal Investigator for the Transformer Toolkit project. I am back again today to do a quick video tutorial. Today we're going to be talking about shaping the failure probability curve. We are back in the spreadsheet. We're in the Transformer Purchase Forecasting Guide Assumptions tab. And basically, we're modeling the failure percentage, the failure probability percentage. And so this entire tool is probabilistic, and so we're rolling random numbers. We're evaluating the odds that something will happen based on a probability. We're checking that against the random numbers, and then we're assigning a 1-0 binary output of failure or not failure. And so one part of this is we're incorporating in a typical failure effects mode for transformers. So if you've ever studied product lifetimes or expected useful lives or product failures or failure, DFMEA stuff, you're probably familiar with this curve right here. This is what's called commonly in the industry a bathtub curve. And it has three distinct parts. The first part is infant mortality. Basically, you have a higher, so again, this curve right here is the probability of failure. So the x-axis is time, y-axis is failure rate, failure probability. So there are three distinct parts. The first one is infant mortality. Basically, we're saying when you first get a product, there is an increased chance that that product will fail. When it comes to electronics, this has to do with, things being installed properly, or maybe you have a bad capacitor in there that during testing it didn't reveal itself, but when you get it, it fails right away. For electronics, that is a very short amount of time, that burn-in period. For stuff like transformers, we consider the burn-in period to be more like a year, to be an appropriate number. And so because of those potential manufacturing defects or whatever it may be, there's an increased rate of failure in the beginning. And as time goes on during the infant mortality period, that chance of failure is going down, right? It's more likely to fail when you first get it, then it's going down. And so at the end of the infant mortality curve, you're approaching a stable number. And that moves us on to the second section, which is constant failure rate or the useful life. Basically, it's, the time when you've got over infant mortality and you are seeing a constant failure rate. Typical expected useful life period. This in transformers is a very small number, but for other stuff it can be different. That one is pretty straightforward. It's just a set number that we put into the spreadsheet. And then you have your main failure mode, which is the wear out period, or once it's approaching its end of expected useful life. I'm familiar with lighting. There are reports called the LM79 and LM80, which detail this, a certain lumen depreciation, when you'll expect to see that. For us, it's going to be when we expect a cumulative probability of transformer failure to happen. But basically, it's getting towards the end of its expected useful life. Its probability of failure is ramping up. And for some products, it's this, concave U-shaped curve, parabola. For us, the project team, we studied a few different academic papers on how transformers typically fail. The curve that we found to be most appropriate was sort of this S curve, right? So rather than like one part of a U on the typical bathtub curve, we have an S, right? So your failure is increasing, then boom, it's starting to get real fast, and then it levels off at a constant percentage of increase over time. And so, we have all of the tools to shape this curve within the spreadsheet. This is not a picture, it's a graph that we're modeling. So I'm going to take you through a few different ways to shape this curve. And so I just want to demo this real quick. Typically, like I've said before, we're going to be viewing this window in half screen as we reference other data over here. So we've created a field of view optimization macro button. It basically, if you're checking out other stuff in here, you just press this zoom button that's tucked away here on this left column, and that'll zoom in on everything that you want to see. We're modeling all three parts of the bathtub curve, but because of the way the formulas work with this, we basically have two different sections, and we'll model the middle part based on the scale parameter. As you'll see, it's basically moving the curve left or right. But let's get into it. So the first thing we model is the burn-in period. These three graphs on the bottom are showing how your infant mortality decreases from the beginning of the burn-in period to the end. Right now we have it set as 1 year. If I set it at 2 years, you'll see it's kind of towards the end of this middle graph. It's now like where it bottoms out is not showing on this left graph, because this is 1 year, 2.5 years, and 5 years. I really wouldn't recommend a burn-in period of more than 5 years. All the academic papers we studied, a most appropriate burn-in period is going to be 1 year. So let's change that back to 1. And again, we've included, if you reference your color codes tab, you'll see there's this teal and this orange color. The teal is just default values. It's recommendations, things we think that will work well with the tool. The orange is a required user input. And so rather than have this be teal and just one column, we wanted to keep this here so that you could continue to reference that as you make changes within this tool. Yeah, that's the burn-in period final year. We recommend 1. The initial failure rate, that's the number that pegs here on the left. It pegs it to a certain value. So if I were to make this 5%, it's saying that your beginning infant mortality rate is 5%. Again, studying the literature, we're actually going to make this 1. I think 1 is more appropriate, given what we've seen from actual real-world data from some of the project committee people. But you can make that whatever you want. Maybe you have a different number. Maybe in the future, as we continue to live with this transformer shortage, the manufacturing practices change to get more transformers out of the manufacturing door. Maybe you see a higher initial failure rate and you need to make this 10, or maybe you need to make it 5. Basically, we've given recommendations, but we've empowered the user of the tool to make changes as you go on into the future. Maybe you're watching this video in 2030 and you're still using the tool and things have changed. Well, you can change the tool with them. So the other number here is the desired failure rate at the end of the burn-in period. That's basically just where this curve bottoms out. So if I were to make this 0.3, and it's probably going to say 30, which is going to mess things up. We don't want 30, so because it's Excel and it's weird, you have to do 0.003, I believe. Yep. So yeah, changing it from 0.3 there, or from its initial value of 0.25 to 0.3, let's make it 440 or 0.4%. So it's a pretty low percentage we want it to bottom out at, right? Because we have load-related failure being modeled in another part of this. We don't want to model load-related failure or any of the other things. We just want to model age-related failures. And so that's the number that'll be pegged here on the left side of our bathtub curve. And also going over like the bottom of the bathtub. Let's put this back to 0.25%. And then the decay constant, again, checking our color tab, you'll notice that one's green. It's because this is a calculated value. We don't want to overwrite that. I kept that in there though, so that you can use the goal seek function to seek to a certain number if you wanted to. But again, that is a formula. And in the final version of this spreadsheet, we'll also lock that tab. So if you go to edit it, it should give you an error message that you're trying to edit a locked cell. But to keep going here, I'm just going to unlock this so that we can dive deeper. But okay, so that is the burn-in period. You have full control over the left side of the bathtub curve. The next part, you're shaping both the middle of the curve and the S curve itself, as well as where it maxes out at. So there wasn't a more user-friendly way to do this. The formula is just some insane formula to get this actual curve to graph. It's this right here. It's a 3-part piecewise function with a Weibull distribution in it too. So let's not dive into that because it's not that important. But basically just saying there's a lot of weird stuff happening over here, Greek letters and stuff. The main point that I want you to take from this is we're shaping the width of this S curve, so how wide this S is. So I'll do some different numbers here to give you an idea. And if you, as you get really small, I've included this little example graph of eventually your S curve is going to turn into a different, more U shape, which is fine, but it's not necessarily what we want. So you kind of want to avoid those really low numbers. You want your curve to be more, let's just do a few numbers here. 3. I would say probably, 4 or 5 is the lowest you want to go, and I wouldn't even do that. I'm more like in this range here. Sorry, I was adjusting the wrong variable. Let's go back and do some different numbers. So like 0.5 is going to give you that U, 0.75 is going to be a different U. But honestly, I'm thinking for our purposes, let's make this 25 here so we get zoomed out. I think, the 3+ range is going to be good for you. But so as you can see, it's S-curve width is what we're changing here. As we go bigger, 15, 20, you don't really need to know exactly what that means. It's why we've included this graph here so that you can see. It's more of a visual shaping, right? So that's adjusting the width. I'm going to put this back to 10, I think. Let's see. Let's make it 7. I think 7 is a good default value. And again, as you'll see, there's no I'm not pegging it to a hard number. It's kind of just a visual thing. And then you have the S-curve location. So you'll notice here, this is going to move it left or right. So let's make it 20. Let's make it 40. This one, it is kind of helpful to know exactly what it is. It's the scale parameter. And this is basically the number you enter here is the time at which 63.2% of units will have failed. That would be true if our lambda was 1, but we're not going to, 100. We're not going to, it wouldn't make sense for there to be a 100% failure chance. It's more about the cumulative failures, which we'll get into a little bit later, but basically, yeah, we're moving this around. It's to where 63.2% of this percentage of the transformers fail. So 0.632 times 0.25. But really what it is it's adjusting your, where stuff starts to fail. So if stuff starts to fail at 30 years, you have to make this number 50. Maybe it's more like 40 years where stuff starts to fail, so let's make it bigger. It's not quite big enough, so let's do, let's do 65. So now it's closer to 40 where that failure is starting to ramp up, and you kind of adjust these numbers to where it makes sense. Maximum failure probability, you can change this however you would like. When you type this in, you'll notice there wasn't much change to the curve shape, but what changed was this axis, right? So let's make it 50, so there's that. I think 25% is a good way to approach, is a good number to use there. Basically because I think that is just what makes the graph make the most sense for me. And it has to do with cumulative failures. And so, we can adjust this visually all day long as much as we want. However, I think one other good way to adjust this is, so basically all the tables that are feeding this, this graphic are here to your right, and there's a summary table as well. And we've got two columns. One of them is, this is the probability of age-related failure each year. So in year 30, right now, the way I've got it, let's adjust this real quick. 44, let's make it like that. Let's make it 15. Nope, let's make it 10. That's a curve that I like right there. And so basically this is saying in year 40, if your transformer hasn't failed yet, if you were to like roll the dice probability wise, it's an 8% chance of failure. But the other thing to consider is that those 39 years before year 40, you've rolled some dice too then, right? So you can think about it as a probability of failure that year, or you could think about it as the cumulative probability. Let's make these percentages. So you'll see at year 40, the probability that year is 8%. However, the cumulative probability is 38%. So like there's a roulette analogy to this too. You know, like if it is landed on red 10 times in a row, the chance that it's going to land on red for an 11th time is actually 50%, right? But if you were to roll those consecutively, one after another, what are the odds that it would hit red 11 times in a row? You know, that would be a much lower percentage, right? So kind of the opposite way of thinking of that is that if you roll the dice a bunch of time on a 50 or like a pass or no pass or fail, don't fail basis, you're adding up those probabilities year over year. So if I have 50%, or let's say I have a 20% probability that something will happen, and I run that scenario 5 times in a row, the odds are that it's going to happen one of those 5 times, right? And so that's why this cumulative probability failure column is so important and really pretty interesting. And so if you've watched the shortcuts guide before, you know what GoalSeek is. GoalSeek is a program within Excel that allows you to optimize your variables towards one number. And so let's say that I want to say by year 50, the odds are that 80% of these transformers have failed. You know, basically I can goal seek this number by pressing Alt and then tapping T and G as I'm holding down Alt. And it's saying I want to set a cell to a value by changing another value. And so the two main ways that we can change things here, the ways that I would recommend approaching it, are by changing the width of the curve, or your shape parameter, or the curve location, your scale parameter. And so just the way this formula works, goal seeking by changing the variable, the shape of the curve, it doesn't always conform to an answer, right? The thing that you really want to do is you want to get the right S shape and then move this curve right or left. Move the location, not the width. So going back to our example, let's say I want 80% of these things to fail by year 50, because that's what matches the data that I've observed in the field. That's what I can expect. And I want to model these transformers I have now based on what I know is going to happen. Well, this tool is allowing you to do that in a very technically sound, backstopped way. So the way to do this, we want 80% failure at year 50, the cumulative probability of failure. We're going to hold down Alt, tap T and G. So we're setting this value here. It's given the green dotted lines around it. We want to set this to 80%, but we're not going to type 80 because that would be, it wouldn't be 80%. This requires it as a decimal, so we're going to do 0.8, right? You could do 0.8, I just do 0.80 because it's how I think about it. And then we're going to click in this box and we're going to click on the cell that we want to change. And as I just said, it's kind of a fool's errand to goal seek this shape parameter. You want to find your shape and then goal seek the location. So we're going to click on this box here and then we're going to click OK and see what happens. So it's running these scenarios and it hasn't yet changed the graph yet because you have to press OK or cancel. The thing is though, it's hit my target value. So I'm going to press OK and then you should see things change over here. Okay, so what it did is it moved this graph to the right? It adjusted this variable, so you'll see it's some big, crazy, long decimal variable, right? This variable has changed so that we goal seek to 80%, and we hit it. And this is now the failure curve the shape, and the location that's going to hit your targeted cumulative failure probability. And you'll notice when we've done that, we typed in 80%, right? Or 0.8, but it didn't get exactly to 80%. That is kind of just the way that Excel works. You could, do it again. But it's going to get you close. It's not going to get you exactly there. And that's okay. That's totally okay. If you wanted to get closer, you could type in, 47.6888, whatever, and get you closer. But the thing is, for me, this is good enough. I think it should be for you too. But, consider that for yourself. So basically what we've done is we've modeled via this, Weibull distribution and all of this math to model a scenario that we know is going to be right. What it's saying is in year 50, the thing is your chance that year that it will fail if the transformer has survived up until year 50 is only 20%. But again, we're doing cumulative probabilities, right? And so it's adding up all those probabilities of the rolls before this roll, the roll of the dice before this roll. And this is the way that it's modeled. But in the past, what people have had to do is to write out some crazy long piecewise formula for one transformer. Well, this spreadsheet has allowed you to shape that curve, done the crazy formula, and as we'll see in the next video, it's applied that formula to many transformers, to 80 transformers, and it's modeled that failure for 40 years for each transformer. It's done all this math, and it's spit it out into a very sensical and easy to understand graph of the results that's telling you how many failed each year and the sizes of each transformer that failed. And it's all based on probabilities. And so, as we step through this, I'm going to do Alt-WN to bring up another window, and we're going to put that on the right, this one on the left. As you do this, because it's a probabilistic tool, it's not saying that, yes, it's 100% certain that this many transformers are going to fail. It's giving you the results of one simulation, right? And so one thing that you can do is you can re-roll your random numbers, and that's where this TPFG random tab comes in. So if I click re-roll probabilities, you should see these numbers change. And so, you can re-roll. The probabilities each year are very low, and so you're going to get different scenarios each time. But as we'll go into later, there is another part of this tool which runs 6 simulations and then averages the results of those. It is pretty cool, if I do say so myself. But all that is to say, the good results that we found from this tool is from reading a lot of academic papers, working very, very hard to get this insane formula to work, this 3-part piecewise formula. And then we looked at the data and made sure that it made sense with real life transformers from the people on the project committee. And so it is very possible to break this tool, but as long as you don't stray too far from the recommended values and you're entering in data that's sensical, it's pretty robust. If you want to stick around the default values, it's going to give you reasonable numbers. If you are maybe a more advanced user of the tool, you're going to be able to dive deep and really pinpoint some accurate data. And because this is forecasting, we're basically extrapolating based on a ton of assumptions. You also have to say, the data scientist in me must say, at the end of the day, you can torture the data to make it say whatever you want. And so you want to be narrow-minded with your assumptions and be approaching it from a place of reality. And you want to kind of take it easy on the goal seeking, because you can adjust the variables to make this say whatever you want. So the approach here is to have a clear head as you approach your assumptions. Make sure you're entering in these numbers that are aligned with reality. And then once you get results, try not to goal seek to make it say what you want. But yeah, that has been a quick summary of how to shape your failure, your age-related failure probability curves. It's just one part of the forecasting. There's basically 4 tabs that make up the forecasting. There's inputs, your assumptions, a summary, and then your random number generator. Yeah, it may look like a lot as you're looking through this, but again, I would stress focus on these bolded and underlined points. You're basically adjusting your curve, adjusting your curve here. Let's see if I can get this to work. I apparently can't. You're adjusting your curve, and then you're adjusting its location. And it's really that simple. You're also adjusting the ceiling, I guess, too. But it's pretty straightforward. And I will also say, when I first started using the tool for real-world data myself, as I evaluated actual failures of people on the project committee, it was a little bit overwhelming. But after I modeled a few different scenarios, it becomes really easy. And then you're eventually in here and saying, oh, the cumulative failure at year 40 is this amount, and you're goal seeking this based on different parameters over here, and you can get pretty deep into it. But I think we'll wrap up there. Thanks for watching this video, and good luck using the tool.